Auto reclosers are automatic high-voltage electric switches designed to protect power distribution systems. Similar to circuit breakers in household electrical systems, they shut off electric power when a fault occurs, such as a short circuit. However, unlike household circuit breakers that remain shut off until manually reset, auto reclosers automatically test the electrical line to determine whether the trouble has been removed. If the problem was only temporary, the recloser automatically resets itself and restores electric power. These devices are used throughout the power distribution system, from substations to residential utility poles. They range from small reclosers for use on single-phase power lines to larger three-phase reclosers used in substations and on high-voltage power lines up to 38,000 volts. Standards for reclosers are defined by ANSI/IEEE C37.60. Importance of auto reclosers in power systems. Auto reclosers are recognized by electric utilities worldwide as essential devices for achieving their prime goal, providing maximum continuity of electric service to customers simply and economically. Their importance in power systems can be summarized through several key benefits. 1. Improved power supply reliability. Auto reclosers sense and interrupt fault currents and automatically restore service after a momentary outage. Since most line faults, 80 to 90%, are transient, the auto recloser can quickly restore power, preventing prolonged outages. 2. Reduced outage losses. By minimizing outage duration, auto reclosers significantly reduce economic losses for both utilities and consumers. For single-fed radial lines, this is particularly valuable as it prevents extended periods without power. 3. Enhanced power system transient stability. The use of automatic circuit reclosers on high-voltage transmission lines reduces system oscillations caused by short-circuit faults, thereby improving the stability of parallel operation and increasing the transmission capacity of the lines. 4. Grid construction investment savings. In power grid design and construction, considering the role of reclosers can, in certain situations, defer the need to build double circuit lines, thus saving substantial investment. 5. Correction of false trips. Auto reclosers can correct false trips caused by faulty circuit breaker mechanisms or protective relay malfunctions, further ensuring power supply continuity. 6. Ensuring industrial production. For critical industrial equipment that would lead to plant shutdown if power is lost, such as boiler feed pumps, fuel pumps, or fans, auto reclosers ensure rapid power restoration after temporary faults, preventing disruptions to normal production. How auto reclosers work. Basic principles. The working principle of auto reclosers is based on their intelligent management and restoration capabilities within power lines. Their core function cleverly utilizes the transient nature of power line faults. 1. Fault detection. When a line experiences a transient fault, e.g., due to a lightning strike or foreign objects blown by wind, the protective relaying system immediately issues a command to quickly cut off power, causing the circuit breaker to trip and isolate the fault. 2. Dead time. The recloser waits for a very short dead time, typically 0.15 to 0.5 seconds. This interval is sufficient for the arc at the fault point to extinguish ionized particles in the air to dissipate, and the line's insulation performance to naturally recover. 3. Automatic reclose attempt. After the waiting period, the recloser controller issues another command to attempt to automatically close the circuit breaker, restoring power to the line. 4. Result evaluation. If the line successfully recovers, it means the fault was indeed transient, and power supply is quickly restored without manual intervention. However, if the fault is permanent, e.g., a fallen pole, broken line, the recloser's first attempt will fail, and the protective relay will trip again. 5. Lockout. In cases of permanent faults, the recloser device enters a lockout state, discontinuing further reclosing attempts and awaiting maintenance personnel intervention. This intelligent mechanism effectively distinguishes between transient and permanent faults, avoiding repeated stress on equipment due to persistent faults while maximizing power supply continuity. Types of auto reclosers by design and operation. Auto recloser types by number of phases. Based on the number of phases they control, auto reclosers can be classified into three main types. 1. Single-phase reclosers. These are used to protect single-phase lines such as branches or taps of a three-phase feeder. They can also be used on three-phase circuits where the load is predominantly single-phase. When a permanent phase-to-ground fault occurs, one phase can be locked out while service is maintained to the remaining two-thirds of the system. Due to their lighter weight compared to larger three-phase reclosers, single-phase reclosers are typically mounted directly to the pole or substation steel structure individually by the built-in mounting hanger bracket. 2. Three-phase reclosers. These are used on three-phase circuits to improve system reliability and where lockout of all three phases is required for any permanent fault, to prevent single-phasing of three-phase loads such as large three-phase motors. The mode of operation is typically three-phase trip and three-phase lockout, where all contacts open simultaneously for each trip operation. The three phases are mechanically linked together for tripping and reclosing, operated by a common mechanism. 3. Triple single reclosers. These are electronically controlled and have three modes of operation. Three-phase trip and three-phase lockout. All three phases simultaneously trip on an overcurrent, reclose, and sequence together. Single-phase trip and three-phase lockout. Each phase operates independently for overcurrent tripping and reclosing. If any phase sequences to lockout condition, due to permanent fault, or if lockout is locally or remotely asserted, the other two phases trip open and lock out. Single-phase trip and single-phase lockout. Each individual phase trips and sequences to lockout independent of each other. This is primarily for residential loads and/or where single phasing of three-phase loads is protected by other means. Auto recloser types by power source configuration. Based on the power system structure and configuration, reclosers can be categorized as 1. Single source feeder lines. These typically only require a standard three-phase single-shot recloser. The configuration is simpler as there's only one power source to consider during reclosing operations. 2. Dual source feeder lines. These require synchronous check reclosers to address synchronization issues between the two power sources. The recloser must ensure no voltage verification and synchronization verification before closing, ensuring safe operation when multiple sources are present. Auto recloser types by number of operations, based on the number of reclosing operations they perform. 1. Single-shot recloser. This method is primarily adopted in many power systems, allowing only one reclosing attempt. This approach is often used in transmission systems where system stability is a primary concern. 2. Multiple-shot recloser may be applied in certain specific operational scenarios, particularly in distribution systems where higher success rates for clearing transient faults are desired. These typically attempt to reclose 2 to 4 times before locking out. The success rate of automatic circuit reclosers is influenced by various factors such as voltage level, line structure, main fault types, and weather conditions. According to industry statistics, the success rate generally ranges from 60% to 90%. Auto recloser control types. The intelligence that enables a recloser to sense overcurrents, select timing operation, time the tripping and reclosing functions, and finally lockout is provided by its control. There are two basic types of control schemes. 1. Hydraulic control, used in most single-phase reclosers and some three-phase reclosers. It's built as an integral part of the recloser. With this type, an overcurrent is sensed by a trip coil connected in series with the line. When the overcurrent flows through the coil, a plunger is drawn into the coil to trip open the recloser contacts. Timing and sequencing are accomplished by pumping oil through separate hydraulic chambers or ducts. 2. Microprocessor-based or electronic control. These are housed in a cabinet separate from the recloser and conveniently permit changes to operational settings. A wide range of accessories is available to customize the basic operation, solving many application problems. Compared to hydraulic controls, they are more flexible, more easily customized and programmed, and have advanced protection, metering, and automation functionality. Microprocessor controls typically utilize PC-based interface software to configure control settings, record metering information, and establish communication parameters. Auto Recloser interrupting mediums. The medium used for interrupting the arc during fault clearing varies between recloser types. 1. Oil interrupters. Reclosers using oil for current interruption use the same oil for basic insulation. Some reclosers with hydraulic control also utilize the same oil for timing and counting functions. 2. Vacuum interrupters. These provide fast, low-energy arc interruption with long contact and interrupter life, low mechanical stress, and maximum operating safety. With arc interruption taking place in a vacuum, contact and interrupter life far exceeds other interrupting media. Depending on type, a vacuum recloser may use oil, air, or epoxy as the insulating medium. In-depth explanation of delayed auto reclosers, DAR. A delayed auto recloser, DAR, is a specialized type of automatic circuit breaker control that opens when a fault occurs, then waits for a deliberate preset delay, dead time, and then attempts to reclose the breaker automatically. If the fault is transient and has cleared, power is restored. If the fault is permanent, the breaker trips again and may attempt more reclose shots before it finally locks out. DAR is a key component in transmission and distribution protection philosophy, particularly on overhead lines, where most faults are temporary. Unlike fast reclosing, which attempts to restore power almost immediately after a fault, DAR intentionally introduces a delay to ensure system stability and proper fault clearing. Definition and core components. 1. Recloser/Auto Recloser. An auto recloser is a circuit breaker equipped with control logic allowing it to trip instantaneously or through protection relays, wait for a programmed interval, dead time, and attempt an automatic reclose. This can happen without operator intervention, using logic built into the relay, recloser controller, or SCADA system. 2. Delayed auto reclose. A delayed auto reclose means that, instead of trying to reclose immediately, fast reclose, the system applies a deliberate pause, the dead time, before reclosing. The delay is typically hundreds of milliseconds on HV transmission fast reclosure. Several seconds for delayed reclose, multiple seconds up to tens of seconds. In the UK transmission context, 10 seconds is a common benchmark in policies, as it gives the system time to stabilize and deionize. 3. Multi-shot reclose. DAR often includes multiple attempts. First shot, after dead time. Second shot. Third shot. Lockout if the fault persists. Each shot can have its own delay and protection sensitivity, allowing for increasingly sensitive fault detection with each subsequent attempt. Purpose of the delay in DAR. The dead time in DAR serves critical electrical, mechanical, and system stability purposes. 1. Clearing transient faults. 80 to 90% of OHL faults over headlines experience many temporary faults, most clear within milliseconds to a few seconds once the line is de-energized. The dead time allows lightning strikes, flashovers from animals, tree branches brushing conductors, wind-blown debris, temporary insulator contamination, arc deionization, ionized air becomes insulating again, mechanical removal of temporary contacts, damping of fault-induced voltage disturbances. 2. Preventing reignition of the arc. When an arc occurs, the surrounding air becomes ionized. If you reclose too quickly, the arc path may still be conductive, leading to immediate reflash and another trip. A few seconds of dead time allows cooling of the arc path, deionization of the air, restoration of air dielectric strength. 3. System stability, especially UK transmission in transmission systems. After a trip, a delayed reclose gives the grid time too. This is why UK NGESO policies sometimes mandate 10s minimum dead time for certain lines. Synchronous generators may deviate in angle. Power flows redistribute. The system may experience oscillations. Recover synchronism. Stabilize voltage and frequency. Allow system damping. Technical parameters and protection logic of DAR. 1. Dead time, the time between trip and first reclose. Examples in UK practice. Transmission, 10 seconds typical minimum. Distribution PMAR, 1 to 5s for first shot, longer for second/third. Primary CBTDR, 15 seconds, SCADA controlled. 2. Reclaim time, after a successful reclose, breaker closes and stays closed. The relay waits a reclaim time, e.g., 20 to 60s. Then resets the shot counter. Ready for a new sequence of faults. This prevents reclose sequences from running too often. 3. Number of shots, typical UK settings. 2 to 3 shots on transmission. 3 to 4 shots on distribution PMARs. 1 shot on some primary CBs, depending on philosophy. More shots equals higher chance of restoring supply, but greater mechanical wear and power quality risk. 4. Protection curves and coordination. Reclosers may include settings must coordinate with, for example, instantaneous O/C, IDMT O/C, sensitive earth fault, directional EF in some networks, downstream fuses, sectionalizers, upstream relays, transformer protection. First shot fast trip, clears transients. Subsequent shots delayed trip, coordinates with fuses. 5. SCADA integration. Modern UK networks use remote switchable and remotely configurable reclosers. Enable/disable auto reclose. Adjust dead times. Apply one shot to lockout for maintenance. Provide live telemetry, fault currents, sequence events, voltage. Applications, benefits, and future trends of DAR. How DAR is used in the UK. DAR is implemented differently across various voltage levels in the UK power system. 1. Transmission, 275/400 kV and 132 kV in Scotland. Common use of delayed auto reclose on overhead lines. Minimum dead times of several seconds, often 10s. Ensures stability and coordination with inter-area power flows. Typically 2 to 3 shots with carefully coordinated timing. 2. Primary substations, 11/6.6 kV. UK power networks and others use telecontrol delayed auto reclose, TDR. Works via SCADA. After a trip, the control system waits, e.g., 15s, then sends a close command. Used on primary CBs feeding large distribution areas. Reduces outage time if the fault was transient. 3. Distribution pole-mounted reclosers, PMARs. Standards such as SP Energy Networks ESDD 02-011 specify multi-shot reclose, often 3 shots. Defined dead times for each shot. Coordination with fuses and sectionalizing links. PMARs often provide instantaneous O/C, IDMT O/C, earth fault, cold load pickup logic, SCADA telecontrol. Example hardware/products for DAR. Several manufacturers offer DAR solutions tailored to UK requirements. 1. Schneider Electric, Set Series. Solid insulated PMAR. SCADA ready. Multi-shot reclose. Custom dead time settings. 2. UK-specific pole-mounted reclosers. Designed for 11 kV and 6.6 kV networks. Remote control plus automatic reclosing. Integrated protection, O/C, EF. Full DAR logic included. 3. Modern relay-based DAR. Numerical relays, Siemens, GE, ABB, SEL, with built-in auto-close logic. Used in primary substations and transmission switching bays. Advanced protection features and communication capabilities. Benefits of DAR in power systems. The implementation of DAR provides numerous benefits to power systems. 1. Improved reliability. By automatically clearing transient faults, DAR significantly improves the reliability of power supply, especially in areas prone to temporary faults. 2. Reduced outage duration. Instead of waiting for maintenance crews to restore power after temporary faults, DAR automatically restores service within seconds to minutes. 3. Enhanced system stability. The deliberate delay allows the system to stabilize before reclosing, preventing oscillations and maintaining grid stability. 4. Better coordination with grid protection schemes. DAR can be coordinated with other protective devices to ensure selective operation and minimize the impact of faults. 5. Cost savings. By reducing outage duration and frequency, DAR minimizes economic losses for both utilities and consumers. It also reduces maintenance costs associated with manual restoration of service. 6. Extended equipment life. By preventing repeated stress on equipment due to immediate reclosing on permanent faults, DAR helps extend the lifespan of power system components. Future trends in DAR technology. The field of auto reclosers, including DAR, continues to evolve with technological advancements. 1. Enhanced communication capabilities. Integration with advanced communication protocols and IoT technologies for real-time monitoring and control. 2. Artificial intelligence and machine learning. Implementation of AI algorithms to predict fault types and optimize reclosing strategies based on historical data and real-time conditions. 3. Improved fault location technology. Advanced fault location algorithms to quickly identify the precise location of faults, enabling faster repairs for permanent faults. 4. Self-healing grids. Integration with broader self-healing grid initiatives that automatically reconfigure the network to isolate faults and restore power through alternative paths. 5. Environmental adaptations. Development of reclosers better suited to extreme weather conditions and climate change challenges. 6. Cybersecurity enhancements. As reclosers become more connected, robust cybersecurity measures are being implemented to protect against unauthorized access or manipulation. DAR will continue to play a critical role in the evolution of smart grids, providing the reliability and resilience necessary for modern power systems that increasingly rely on distributed generation and renewable energy sources.